Sure, yeah.
Okay. Okay, then let me start. Okay, today's talk is by Tyler Helmuth, and the title is Efficient Algorithms for Low Temperature Spin Systems. So please.
Okay, so thanks a lot for the invitation to speak and opportunity. So I'm going to tell you about something that's sort of maybe adjacent to mathematical physics as opposed to mathematical physics proper. So it will be maybe a somewhat unusual talk in that probably most people here are already quite knowledgeable about the techniques, and what's unfamiliar are the questions. So I'm mostly going to spend time talking about the questions and what we'd like to answer, as opposed to talking about the overview of the techniques, because I think that would be fairly familiar. But we'll see. And of course, at any point, ask questions and feel free to interrupt. Okay, so efficient algorithms for low temperature spin systems. Let's first just agree on a couple of spin systems that I'm going to talk about. Okay, so I'm always going to be talking about discrete spin models, and I'm going to be talking about finite graphs. And, you know, when I talk to computer scientists about this, I always make the joke that when I say finite graph, I really mean ZD. There's only one graph in my mind, or one family of graphs, the hypercubic lattices. But from the computer science point of view, you want to think that there's any finite graph, which is why I drew this funny looking graph in the bottom corner. So one model I'm interested in is the POTS model, which is just going to be a coloring of the vertices of a graph by Q colors. So the Q colors you can think of, if you want, as being, you know, 1, which is maybe red, 2, maybe 2 is blue, and so on. And we want the colorings to be weighted so that we see the same color appearing fairly often. And the way we do that is by introducing the energy of a coloring to be the number of bichromatic edges. So this is something that you've seen before, I suspect. And then we declare the probability of a particular coloring, which depends on beta and Q. It's just exponential minus beta times the number of bichromatic edges, normalized by an appropriate partition function. And throughout this talk, whenever I talk about the POTS model, I want it to be the POTS ferromagnet, so beta is going to be positive. So we want to see similar colors. So bichromatic edges, I think, is familiar, but just to be completely sure, let's make a little example on the picture. So if that vertex was colored red, and this one beside it was colored blue, then I have a bichromatic edge here because its endpoints have been given different colors. Okay, so this is the ferromagnetic POTS model with Q colors, and I think it's fair to say that we know an enormous amount about it. In fact, it's maybe one of the models we have the best control over. So at least if we are talking about ZD, we know, that there's phase transitions. We know the order of the phase transition in many cases. For example, when Q is large, it's a first order phase transition, while if Q is 2, it's a second order. Q is 2 is the Ising model. We know things like sharpness of the phase transition and many other things. Okay, so this is an extremely well-studied model, and we sort of understand what to do and how to study it. Of course, from the computer science point of view, they're interested in basically arbitrary graphs, and then it's less clear what we know. So let me introduce the second discrete spin model that will sort of play a role today. It's called the hardcore model. And again, this is one that many of you have heard about before, so I'll be a little more brief. So now this bins take values of 0 or 1, where I think 1 represents a particle being present and 0 means there's no particle. And then the probability of one of these configurations, which I denote by I, because I want it to be an independent set, is lambda to the size of I, where the size just means the number of ones. And then I require that the set is independent. And I normalize. And independent means no adjacent ones. Okay, so just again to be sure that we agree, let's color in an example of an independent set on this graph here. So this is an independent set with 2 items, and I can maybe manage to color one more if my iPad will cooperate. Okay, it won't cooperate, so we'll stop at 2. So there's an independent set of size 2. And I could not make this one into a pink occupied site because they would be neighbors, so that wouldn't be independent. So this is something that we know less about than the Potts model, but we still know quite a bit on ZD. So on ZD, we at least know that there is a transition when D is at least 2. And we know sort of the extreme, we know that we can understand the behavior in the extreme values of lambda. So we sort of understand the low and the high density behavior. So we sort of understand lambda small and also lambda very big. This model is not nearly as well understood as the Potts model, though. So for example, we don't know that there's a unique phase transition. There's quite a few seemingly challenging open problems about it. Okay, but that was just to introduce the models. Now I want to sort of go on to tell you about the questions, which are different than the usual ones. I suppose, though, if there's questions about the models, this would be the time to ask them to be sure we at least agree what we're talking about. Okay. So whenever you have a discrete statistical mechanics model, there are sort of some computational questions that you can ask. Let's set up the rules of the game first. So the rules of the game are that you pick your model, you pick your model parameters, and you pick some set of allowed graphs. Okay, so script G for me is the set of allowed graphs. So for example, we could choose the Potts model. I could choose beta to be, say, 47.17. I could choose Q to be 23. And I could choose script G. Well, I could say choose it to be all finite graphs. Or if I wasn't feeling so ambitious, because that's a very big set of graphs, I could choose something like, say, G delta, which is finite graphs of max degree delta. Okay. So those are 2 possible choices. And once I do that, there's 2 problems associated with them. So in advance, we're fixing all of these things, and then the task is the following one. So one is counting, where by counting, I really mean weighted counting. So that's an algorithm that takes G in this set G, and it outputs the partition function. And the other problem is sampling. And if you like, what that is it's an algorithm, and it's a randomized algorithm. So it has a source of randomness that outputs a spin configuration sigma distributed according to the probability law of the model I've chosen with the parameters I've chosen. Okay, so again, the sampling algorithm is given a graph because it has to output a spin configuration on that graph. Okay, so those are the two problems that we're interested in, formulated very naively. So if you formulate the questions like this, there's really nothing interesting to say. Of course, you can do this. You just list every possible configuration, compute the weight, and add them up. Okay, you're never going to finish doing that, as you know. There's exponentially many configurations, so this is not a practical process. So what we want to do is sort of relax our requirements in a way so that efficient algorithms actually might exist. And this is the subject of approximate counting and sampling. Okay, so let's first talk about counting in the approximate form. So the way it works is that I can't expect to get the exact answer with an efficient algorithm. This is something that's been known for a long time in the computer science literature. It was sort of an important discovery, I guess, of Leslie Valiant. So the approximate version is as follows. So you get given some tolerance, epsilon, and you get given a graph in your collection. And what you want to do is not output the partition function, but instead some number z hat, such that you're very close to the partition function in the sense of a multiplicative approximation. So you want the ratio of z hat to the true partition function to be between e to the minus epsilon and e to the epsilon. And there's a requirement, which is that you want it to happen quickly. So we want it to happen in time polynomial in the size of the vertex set of the graph and 1 over epsilon. So what this means is that you get an amount of time polynomial in the size of the graph. That part is pretty clear. But also, if you ask for more accuracy, you get more time. And here, epsilon is allowed to depend on the size of the graph, in fact. So you could ask for epsilon to be, 1 over n squared if there's n vertices. That's permitted. Okay, so this, the existence of such an algorithm is usually called a fully polynomial time approximation scheme, or FPTAS. And if you use randomness in your algorithm, then the T becomes an R. Fully polynomial time randomized approximation scheme. Okay, that's the counting problem. And the sampling problem is similar. Again, we have to introduce some tolerance and let our amount of time depend on that. So again, given positive epsilon, any of the allowed graphs, we have to output sigma hat, a spin configuration. Such that the total variation distance between our output and the truth is at most epsilon. And again, it has to run in time polynomial in the size of the graph and 1 over epsilon. And this is called an efficient sampler. Okay, so if you've never seen these problems before, this might not be so obvious, but these problems are basically equivalent. If you, in many situations, if you have an FPTAS, an efficient counting algorithm, you can use it to produce an efficient sampler. And conversely, if you have an efficient sampler, you can use it to produce an FP task or an FP-RAS. So for most of this talk, I'm going to focus just on the case of counting because it's slightly simpler to describe, but you should have in the back of your mind that if you can do one, you can probably do the other. So what's an important example of such an algorithm? Well, Markov chain Monte Carlo. Okay, so this is a very popular way to try and get an approximate sample from some distribution. Of course, we know that if you run it for long enough, you will get it. But really, if you want it to be efficient, what you're saying is that you have a bound on the mixing time in most situations. Okay. So Markov chains are one way to produce such algorithms, but and of course, that's a subject in its own right, is to study mixing times of Markov chains. But from the sort of broader point of view, you shouldn't restrict yourself to such algorithms, because the problem you really want to solve is how do you approximately sample? I mean, that's the truly practical problem that shows up in many parts of science. Okay, so because I'm sure you've all seen or heard talks or worked on the idea that for many statistical mechanics model, if you're in a high temperature regime, you can prove mixing time bounds so that Markov chains rapidly mix, and they'll give good algorithms for this. And you're probably all also familiar with the fact that, if you look at statistical mechanics models on ZD, for example, Markov chains will mix slowly once you're in the phase coexistence regime at low temperature. So if you don't start, the worst case running time will not be polynomial. It will instead be exponential in the volume. So we can't expect to use Markov chains and mixing time bounds to get algorithms at all temperatures or all values of parameters. And once you learn that, it's kind of disappointing because it's we understand the model pretty well on ZD, so why don't we have an algorithm? And what I want to tell you next is a surprising discovery of something that goes under the name of a computational phase transition that says that the thing that happens for Markov chains is not just you should really worry in some sense. So first, maybe a warning is that computational phase transition, the first time I heard it, I sort of thought, people must just be saying phase transition for no particularly good reason. And it's not like a phase transition as we think about them, but it is related. And I think it is an interesting idea. So let me describe it to you. I think every now and then I see red numbers popping up. So if there are questions in the chat, I just can't see it at the moment. So if someone could tell them to me, I can try and address them if needed. Okay, so to describe this computational phase transition, let's think about the hardcore model. So independent sets on graphs. I'm going to fix a maximum degree of the graph, delta. In other words, the set of...
So sorry to interrupt.
Yeah.
Also, Takashi. Robert Mackay was asking about the total variation distance, but it was not necessarily a suitable measure to use.
Certainly you could choose others, but this is sort of the standard in the field. So if you like, though, I don't think it's going to be super sensitive to the one you choose unless you choose something extremely forgiving. But maybe the details of that we could discuss later. Okay, so I fixed delta, and I'm going to restrict my inputs to be graphs of maximum degree delta. And then I introduce this parameter lambda star delta, which is, okay, it is what it is. And this might be familiar to you because this is the uniqueness threshold. On the delta regular tree. So this is the point at which if you look at the hardcore model on the delta regular tree, you go from having a unique Gibbs measure to having multiple Gibbs measures. Or if you like, from having decaying correlations to strong correlations, rapidly decaying to strong correlations. So the computational phase transition sort of refers to the following two results, which are, I think, quite an attractive combination. So one theorem, due to Weitz, says that if you look at a lambda less than lambda star, so you're in sort of a high temperature regime on the tree, then in fact, there is a fully polynomial time approximation scheme for this class G delta. So you give me any graph with max degree at most delta, and you can efficiently give as accurate an approximation as you want to the partition function. And the counterpart is due to Alan Sly. In the form I'm stating it, it involves refinements of Sly and Son, Glannis, Stefankovich, and Pagoda, which is that if lambda is bigger than lambda star, then, so briefly ignore this middle condition, then there is no fully polynomial time approximation scheme. Okay, so the existence of an approximate counting method for this problem is very sensitive to the value of lambda. And the point at which it goes from existence to non-existence is exactly where there's a phase transition on the delta regular tree. So the condition I erased is that if you want to say that there doesn't exist such a thing, you have to rule out the existence of an algorithm. And to do that, you usually need to make some assumption about computational complexity. And here the assumption is that NP is not RP. So RP is the class of decision problems you can solve with a randomized polynomial time algorithm. So you should think that this is about as likely as P equals NP, and I'll let you assign your own prior to that. But I think sort of the view in the field is that if you can show that something is NP, that means there's not going to be a polynomial time algorithm. Okay, so this is, I think, it's crucially very different than a phase transition in the sense of physics, because here we're talking about this enormous set of graphs, and that's playing a role. But nonetheless, it is a very sharp result that says that there's something interesting happening. And if you like, what you should think, or one way to think about this result, especially of Weitz, is that it's an extremely strong uniqueness result. It really gives a point at which there's, a high temperature phase on all max degree delta graphs. Okay, so when I first learned this, I was quite taken by it and very surprised. And I think it immediately raises some questions. So one question is that if you are a person who likes to be very optimistic, you want to know when you can sample from distributions accurately. It's not so interesting to know that you can't do it. That just says you can't do something. And, okay, that's useful information, but you want to know what problems you can solve. So can we avoid the negative result, the non-existence, by either restricting the set of graphs, and if necessary, maybe also taking lambda to be large? So another way of phrasing this is that the result of Sly sort of suggests that there's some graphs on which we can't really efficiently compute the partition function, or more accurately, there are some families of graphs in which we can't, because this is a question about the dependence on a parameterized family of problems. And we'd like to know what are those instances where we can't succeed, and when can't we succeed? Another question is, this was a result about the hardcore model, but maybe this phenomena occurs more broadly. Okay. So here's a conjecture from the computer science community that gives some extra motivation maybe to the first question above. The conjecture is the following. So restrict yourself for the hardcore model to the input graphs being bipartite. So this, you might imagine, should make your life easier, because if you think about a very dense independent set on a bipartite graph, that's a simpler thing than a maximal independent set on a general graph. So if you want to find a maximal set on an independent set on a general graph, this is something you can't do. It's an NP hard problem. But on a bipartite graph, there's a polynomial time algorithm to find a maximal independent set. And the conjecture then is that if you restrict to bipartite graphs, then there still isn't an FP task. So it's still not an easy problem, but it's also not to believe to be a hard problem. So this conjecture says something like, at least informally, that approximately computing the partition function for bipartite independent set is not polynomial time, but it's not NP. So it's intermediate to those complexity classes. That's an informal statement of what this conjecture says. So in fact, this is a very natural problem. It's usually referred to as sharp bis or number bis, meaning that there are many other problems that show up. You know, for example, computing the partition function of the Wilhelm-Rowlandson model, or, well, there's a whole host of problems that are sort of, if you could solve sharp bis, you could solve those problems. So it defines its own complexity class. And here's an example of a problem that falls into that class that I think is quite interesting. So if you take Q at least 3, and you take any beta, and you say take G bipartite, then the Q state Potts model is sharp bis. Meaning it's as hard to devise an algorithm for this problem as it is for independent sets on bipartite graphs. So this is, at least for me, I find it hard to think about all graphs with no restriction on them whatsoever other than being bipartite. So maybe you might prefer to think instead of bipartite graphs of maximum degree delta. And it's sort of equivalent to say, if you can solve Potts at any beta, then you get the above. Okay, so sort of because you can add extra edges to your graph to manipulate beta, fixing the degree and changing beta is sort of the same as choosing a beta and allowing the degree to vary. Okay, so for me at least, this was motivating in the sense that the Potts model is something we sort of completely understand, or we think we completely understand. So what can we do? When can we produce algorithms? And what's difficult about this problem? Or what might be difficult about this problem?
Can I ask a question?
Of course. Go ahead.
When you say compute the partition function, in terms of the free energy, the discontinuity at phase transition occurs in the derivative of that, which means that if you are looking at the free energy per volume, ignoring boundary terms, that it may be easier to compute it. In other words, when you say compute the partition function, is there a difference between computing the leading term partition function per unit volume? Would that be, would there be no phase transition in this versus, say, looking at the boundary term.
Right, so that will play a role in general, but here the point is that when I say compute the partition function, I mean to arbitrary multiplicative accuracy. So you need to see the surface terms.
Yeah. Thank you.
In general, it's not, for nice graphs, you won't need to worry about this surface term. But because we want epsilon to possibly depend on the size of the graph, you can see sort of arbitrarily fine detail.
But epsilon is typically like the surface or like the volume?
So the requirement of the algorithm to form a nice, computational theory is that you really have to allow epsilon to be whatever you want. Of course, once epsilon is, say, exponentially small in the volume, it's very easy because now if you get time polynomial in 1 over exponential the volume, you have exponential time, and then you can just do it by brute force. So the interesting range of epsilon is sort of, from exponentially small up to constant. But it's a requirement that the algorithm is polynomial time all the way in between.
Thanks.
Okay, so now we're going to come to familiar tools. But just by way of saying how I got started on this, sort of is a method that came up in computer science or combinatorics, but due to Sasha Barvanok, but that you'll recognize as a result about statistical mechanics. So he was interested in approximating partition functions for some problem, and he came up with the following observation or lemma, which is that if you have a degree n polynomial, z, so you should think of this as being your partition function. Say if you have a finite, any finite partition function is just some polynomial, an appropriate parameter. And if you know it is non-vanishing in some neighborhood of the origin, which I call 1 plus delta times lambda for the radius of that ball, then you get a very good approximation to the log partition function, error epsilon, if you look at the mth Taylor polynomial of the log partition function, provided m is of order log n over epsilon. Okay. So this is actually fairly simple. To prove this, you just write that the polynomial is a product of 1 minus lambda over its roots, and Taylor expand the logarithm. So there's nothing fancy happening here. Of course, what we know is happening is that if you have no zeros near the origin, that means that you're in the high temperature phase of whatever this partition function represents. So the only important contributions are from small numbers of particles, which are the initial, what contributes to the initial Taylor coefficients. So sorry, 1 second. The upshot of this is that if you want to get an algorithm, you only need to compute the first order log n over epsilon Taylor coefficients. Okay. The problem, though, is, or a first problem is that you have to do this in polynomial time. And there's a lot of coefficients, unfortunately. So if you have a polynomial of degree n, you should think this is something like, think of the hardcore model. You have an activity lambda per particle. If you made all the activities different, you have n different variables. So the number of possible coefficients up to order log n over epsilon is like n to the log n over epsilon. And this is not a polynomial. So if you want a polynomial time algorithm, there's no way this is going to succeed naively, because even if you could compute each coefficient instantaneously, it would still take you more than polynomial time just to do that for each one. So still, this is a much faster algorithm than exponential time, but it's not quite polynomial time. And to improve that, a first step was made by Pirosh Patel and Husrecht, who noticed some clever identities that would allow them to compute all the necessary coefficients in polynomial time. It was quite clever. But there's a second solution that I guess I came up with Will Perkins and Husrecht, which is that maybe you should interpret this statistically in terms of statistical mechanics. And the way you should really think about it is the following. You have the logarithm of the partition function. You should prove that the cluster expansion converges for this. So I think the cluster expansion is familiar to many people here, but if not, I'll briefly review it on the next slide. So you prove that the cluster expansion converges. That tells you that there's a zero free region, like in Barvanak's lemma. And it tells you that the terms in the expansion for log z, so the Taylor coefficients, are exactly indexed by connected objects. So the advantage of having connected objects is that enumerating connected objects takes exponential time in their size under very general conditions. And then you're in good business, because here, if we only have to go up to objects of size log n over epsilon, it might take us exponential time to enumerate them, but it's still a polynomial in n over epsilon. So the point is that because we only need to compute logarithmically many terms, we can use exponential time algorithms and still remain polynomial. So in fact, if you have a convergent cluster expansion, you also get the error estimate from Barvanak's lemma for free. So really what was happening in these algorithms is that they were rediscovering the cluster expansion, but from a different point of view. So as a brief remark for anyone who doesn't quite remember the cluster expansion or hasn't heard about it, here's a crash course in the very, very simple cluster expansion that I mean. So there are many cluster expansions in mathematical physics, and this is sort of the abstract, simplest one you can think of, where you're sort of expanding about counting measure. So you have some set of objects that you call polymers. It's just an abstract set. And you have a notion of them being incompatible, which you should sort of think about as them being occupying the same physical space. And you also have some weight function that takes each polymer to a weight W gamma. And if you're given that, then for any finite subset of the polymers, you form a partition function where you sum over subsets of polymers that are compatible. So not incompatible is compatible, product of the weights. And if you think about it, all this is the independent set, or the hardcore model that we introduced on the second slide. It's just on a very general graph. So instead of being given a graph and looking at the independent sets, I'm just telling you the relations between the things. So that's a polymer model, and the cluster expansion, if you like, is this result due to Meyer, who said the logarithm of the partition function is a sum over connected clusters, some combinatorial factor called the Ursel function associated with the cluster product of the weights in the clusters, where what a cluster is that if I have some polymer A1, A2, A3, a cluster means that they're all connected by this incompatibility relation. So this is a possible cluster. So this series of Meyer is a formal series. So it's a formal computation of the logarithm. And to use it with error estimates, you need to know it is a convergent expansion. And there are many criteria for the convergence of this expansion and convergence of cluster expansions in general. But in this setting, there's a very nice result due to Katetsky and Price. That is what we end up using. Okay, so to sort of summarize this, you can interpret and unify some results about computing partition functions by thinking about them as being results using the cluster expansion. And you get efficient algorithms because, in fact, computing this combinatorial factor can be done efficiently, at least when the clusters are only of size log volume. And computing all of the possible polymers can be done as well, say in a bounded degree graph.
Okay, Tyler,
Yes.
there are several questions in the
Okay.
chat. And the first one is, what's the computer science analog of temperature?
The computer science, so they're happy to count weighted objects as well. So the temperature is like lambda. Lambda small, low density is high temperature. I mean, they would often want to think about it maybe as changing the degree of the graphs and keeping the temperature fixed, but you can sort of swap between the 2 points.
And the second question is there a constraint on the weights? I think about the cluster expansions.
So certainly if you want to prove it converges, you have to show some condition on the weights. And roughly it says that the weights have to decay exponentially fast in the size of the polymer. But I'm going to be, at the end we can discuss exact conditions, but basically you need to have some exponential decay of the weights.
Okay.
Okay, so now I can sort of heuristically at least describe how you do this at low temperatures. And in fact, it was the low temperature problem that got me interested in this, because this result of Sly said there's no algorithms when lambda is bigger than something, but on ZD, if you want to say what does a very dense independent set look like, well, it looks like you mostly occupy all the even vertices or you mostly occupy all the odd vertices. In fact, that's how you prove there is a phase transition. So there's a picture drawn here of a high density independent set where most of the place we just look like we're consistently choosing one of the bipartitions of ZD. But occasionally we make some mistakes. So here we're missing a particle, and here we have a particle on the wrong sublattice. So if you want to prove that there is a phase transition, well, what you do is you sort of think that I want to make the new particles the deviations from the optimal configuration. So you extract from the partition function lambda to some power of the biggest possible independent set, and then you sum over all independent sets, lambda to the size minus the max. And then you devise, and this part I'll be a little vague about, an expansion that says that you can group these things together into polymers or collections of polymers associated to some weight, where these weights now, so this is the weight of a deviation from optimal. So if you like, this is sort of, okay, there are many ways you can derive such expansions, but most commonly they occur in generality in Pirogov Sinai theory. So this is a way to control the low temperature phase diagram of a statistical mechanics model. And this looks basically like an independent set model or a polymer model as I introduced it on the previous page. The difference is that these weight functions could be complicated. So here, for example, if I wanted to look at the deviation from the ground state, I sort of have this region where I'm making errors. But inside where I'm making errors, there are lots of possible errors. So in some sense, this weight is itself a partition function or a ratio of partition functions. Nonetheless, we should be optimistic. We have this z tilde of lambda inverse, which is everything other than this part here. And we want to say, can we compute? Z tilde. If we can compute z tilde, then we can approximate the partition function. And basically, because of what I just said before, we sort of know the answer is yes if we can do the following things. Well, one, we need it to be a polymer model, which means that the allowed collections have to be defined by some pairwise disjointness condition. We need to know that the weights are small enough to have a convergent expansion, so exponentially small in the volume or in the size of the polymers. We need to know we can enumerate all of the polymers that we need to. We need to go up to logarithmic size, so we need to have an exponential time algorithm. And lastly, now we have these weight functions, and we need to know we can compute them in exponential time in this size. So by far, when you're thinking about statistical mechanics results, you don't have these last two conditions. You only have the first two. And this part is non-trivial. But understood at this point. It's Pirogov Sinai theory. And, in the version sort of devised by Zherednik. So the only thing that's sort of subtle here now is that, okay, for a particular model, you have a definition of what the polymers are, and you have to devise a way to enumerate them, and that might be complicated. But it's usually doable. The trick is really this W. So this W encodes the weight of deviations, and itself will actually often be, it contains partition functions in the weight. So the problem is that you're just not going to be able to do it because you can't exactly compute partition functions. This is the whole problem. We're trying to come up with efficient approximation schemes because we can't ask for exact computations of partition functions. So we have to actually replace 4 with 4 prime, which is that you can compute approximately in exponential time. So what I mean by this is that if you take the cluster expansion and you can only approximately compute all the weights of the polymers, as long as that approximation is good enough, the first log term, log n over epsilon term, still give you a good approximation scheme. And the reason that this is good is because now if this weight contains a partition function, we're okay. Basically because you work inductively. For the smallest size of polymers, you can sort of just explicitly compute the weight. And then if you have an algorithm up to some size to compute the partition function approximately, then when you go up to the next size, you can use your previous algorithm inside. And this is actually very similar to the inductive analysis of Pirogov Sinai theory. Okay. So if you've never seen these low temperature expansion methods, this is a little too fast, but I think it gives you the idea that at low temperatures, you can sort of treat it like a high temperature problem. So as an example in this paper with Will Perkins and Rex, we showed how you can use this to approximate the partition function, say, in boxes in ZD if you put ground state boundary conditions. So this raises the question, though, what happens at intermediate values of lambda? So this is only when lambda is extremely large to prove that the expansion converges. What happens in between? So at this point, I should ask, should I stop now or should I stop at the hour? I can't hear you, Takashi, you are muted.
Well, at an hour, right, Daniel?
Yes, indeed. Usually we are not too strict about the time anyway.
Okay. So I will take a few more minutes then to sort of go slightly further. So intermediate lambda is going to be difficult for the independent set model or the hardcore model because we don't even understand what happens there probabilistically on ZD, so even on nice graphs. But if we return to the POTS model, we're in a better situation. Because for the POTS model, there's been this theory developed. If you take Q very large, you can use 1 over Q as a small parameter for an expansion method instead of using the temp beta as a small parameter. And the basic way that this works is that if you use 1 over Q as a small parameter, then what you can do is you split up the partition function into 3 pieces. There's an ordered piece and a disordered piece and an error piece. The ordered piece you should think of as being configurations where most of the colors are the same. So you see a dominant color. The disordered ones are the ones where you see roughly uniform spread amongst colors, and the error is everything else. What you do then is show that you have a convergent expansion for the disordered piece that goes that includes the critical value and goes past. And you also show that you have a convergent expansion for the ordered piece that overlaps. And the error is indeed an error. So what this means is that basically by the methods I just described, if you can do this, you can efficiently approximate this part of the partition function in this whole regime. And you can approximate this part of the partition function in this whole regime, which means actually that you can approximate the whole thing because this is something that you're able to throw away.
Eiler, so
yes.
do you mean that this trick works for a fixed lattice structure and for sufficiently large Q, depending on the lattice?
So in this setting, it's a vague statement, which is not precise. And to make it precise, you'd better fix the lattice structure and then choose Q appropriately.
Okay.
Yeah. So the precise statement for ZD would be that you fix D and then you choose Q large enough depending on D, and then this works.
Okay.
And this is, so if you like, this is due to many people. I think the first version is Kotetsky and Schlossman, and then there are many other authors who developed this. And basically what you get is that you get complete control of the phase diagram on ZD or say on finite tori. The version that I like, because it's what I used in a paper that I'll describe in a moment, is due to Borks, Chase, and Tedley, and they use the POTS model in the random cluster representation. I don't want to go into it if it's not familiar, but just to say that there's a price to pay for this, which is that when I was discussing in the Potts model, there's sort of this symmetry between all the colors. And at very low temperatures, they're all sort of equivalent. It's just a symmetric change. And this was useful when you want to compute these weights, which possibly involve partition functions, because you actually have convergent expansions for each partition function. But when you work in the random cluster representation, now there's an unstable ground state. And this leads to some difficulties in step 4 of my schema for how to find an algorithm. But it's something that you can overcome. And in a paper with Borgs, Chase, Will Perkins, and Prasad Tatali and myself, we showed that on ZD, or actually on tori, so we need to take tori because we need a sequence of finite graphs to ask about algorithms. If you fix the dimension and then you take Q big enough, then for every single temperature, including the critical temperature, there is an efficient algorithm for approximating the partition function. And there's also one for sampling. So from the point of view of computer science, ZD they think is a bit weird. But by this general schema I outlined in another paper with Matthew Jensen and Will Perkins, we showed that if you fix some delta and look at delta regular random graphs, you can do a very similar trick. So if Q is big enough depending on delta, then for every temperature, there is a fully polynomial time approximation scheme for delta regular random graphs, at least when delta is at least 5. Okay, so also for graphs that look really random, you can devise algorithms for the Potts model at any temperature, at least for big Q. So this sort of raises to me some questions that I'm going to finish with. So one question is, can you do better? Are there faster algorithms? Because these algorithms I've described are polynomial time, but they're, pretty horrific. I mean, the polynomials are extremely high degree, and we have to use Q extremely large. So it would be nice to have some more genuinely practical way of doing this. Another question is, can we somehow interpolate between really structured graphs like ZD and random graphs like, well, random graphs? So, from the computer science point of view, these conjectures are about all graphs with just some bound on the degree. So they can be some mix of structured and random and have all sorts of things happening. And right now we're sort of restricted to saying, you better really look random or you better really look structured, and otherwise we don't quite see how to blend the two worlds. And lastly, from the point of view of statistical mechanics, discrete spin models like this are, of course, of significant interest, but so are more subtle models, like models with continuous symmetry. So what's the computational challenge of those models? Is it easier or is it harder? It's not clear to me. Okay, so thanks very much for your attention.
Okay. Any comments or questions?
May I have a question? Ask a question?
Yes, of course.
Yeah. I am very pleasantly surprised by the statement, I guess I missed those, that you have algorithms which converge beyond the range of analyticity. In other words, it reminds me of the discussions of metastability. And the question was whether the free energy in the metastable state makes sense thermodynamically, or is it thermostatically, or does it depend on dynamics? So are you, in a sense, computing metastable states on the basis of certain computational dynamics?
I don't know how to exactly answer that question. I would say here the achievement is not due to me and my co-authors. It's due to this idea of how to get expansions past the critical point is really part of the Pirogov Sinai theory and finite size scaling, where the trick is to extract just the metastable phase and then develop an expansion for that and do it separately for each piece. And if you want, you can sort of change the interaction on large contours in such a way that you can converge past the critical point. And this is what they're doing. So it is some control of the metastable phase, but it's not. I mean, there are still things that I don't understand how to answer about those phases. Like for example, the mixing time of Glauber dynamics in those phases is not so easy to analyze.
Mm-hmm. I mean, it has been an old question passed to me by my thesis advisor to make sense of metastability. And unlike the mean field models, the impression was that there is no natural sense of, say, the free energy is not analytic at that point. And yet there may be sense given to it in relation to some particular dynamics. And I suspect that the computational method here introduces, gives a meaning to it, some meaning to it. It may not be independent of the dynamics. But
I see. So I suppose in some sense that maybe existed. So this paper of Borg's, Chase, and Tedley that I mentioned, they give very sharp estimates of the mixing time of Glauber dynamics on a torus. And this is the reason they developed such a refined theory. So they can say, they can make very precise statements about this error partition function in terms of the bottleneck between the two metastable phases. Mm-hmm. Mm-hmm. So maybe in some sense they're giving an answer to this question.
Thank you.
Thanks.
Can I ask a question? So I want to understand the statement for your second theorem about regular random graph for large Q. So how does randomness mean being used in this theorem? So
yeah, so actually the truth is the theorem isn't about random graphs. The proof is actually about a certain class of expander graphs, and random regular graphs satisfy those expansion conditions with high probability.
Okay, so it means that I can give you a concrete one graph.
Yes.
Okay, not necessarily random, satisfying certain condition, and then you can.
Yes, and actually the conditions that we require, you can also check if those conditions are satisfied in polynomial.
Okay.
So if you actually give me a random realization, I can then say my algorithm works or it doesn't work, and then.
Okay.
So the conditions are sort of that it's not the. It's slightly more than maybe what you've seen an expander be called before, because we need also some notion of expansion on small sets. So it's expansion at two different scales that we need. But a random regular graph is a good expander on every scale. So these conditions are satisfied.
But may I come back again to the previous point? Is it the case that in those expansions you sort of rule out clusters which would correspond to flip, say, of half the volume?
Yes.
So the value of the free energy which is computed ignores what I originally asked about, which was terms of the order of the boundary, essentially. It's not meant as a boundary conditions, but boundary between the two phases into which the system may want to break. Now it's in the computation which extrapolates from very low temperature, from the low temperature, I presume that you ignore the free energy which is associated with the interfaces over which you flip from one phase to another, interfaces which span the size of the system.
Right, so the result is on the torus, and so the interfaces that you're worried about are the ones that actually disconnect the torus. And what's proven by Borg's, Chase, and Tedley is that the contribution, the error, those are all in the error partition function, and it's exponentially small in n to the d minus 1 if n is the side length of the torus.
Yes, exactly. So
and the point here, how we get an algorithm. So I shouldn't have said FP test. I should have said FP RAS, because if you're any smaller than that, as in if the error is smaller than that, then from a computational point of view, because I'm allowed to take time polynomial in 1/epsilon, you can just switch to using the Glauber dynamics, because they do mix fast enough at that point.
So is the message that if you would like to compute the free energy up to orders for which the interfaces of this nature do not matter, you can do it always efficiently. But if you go beyond that, things potentially slow down.
If you go beyond that, because of the sort of accepted definition of approximate counting, it's still okay because you have to give yourself so much more time because epsilon is so small. But it's non-trivial that Glauber dynamics mix that quickly.
Thank you.
So yeah.
Mm.
But that error term, in principle, you could also understand that error term and its leading order and corrections to it by using the methods of Borg's chase Tetely. But it becomes somewhat topologically complicated on the torus.
This reminds kind of works of Leibowitz and Perkus, where they try to define the metastable state, say, of the Ising model as one in which the majority, even if the magnetic field is turned negative, the majority of the spins is still positive, for instance.
I'll have to look. Thanks.
So maybe this is a serious, stupid question, but so what is the main difficulty of, having a result of usual rigorous statistical mechanics like convergence of cluster expansion, and then going from this kind of standard result to the results about these computational algorithms? What is the main difficulty?
So for some expansions now, there's not really a difficulty in the sense that we actually said if you can show Pirogov Sinai theory works, you get an algorithm. We actually did phrase it that way. But if you want to get, so our initial paper with Will and Hustrecht was only dealing with the case where all ground states were stable. And the later one with Borg's Chase and Tetely and Will Perkins and myself, there we had to deal with the fact that there could be unstable ground states. But in some sense, I think we've given a schema that will let you convert any convergent expansion into an algorithm. There were non-trivial things to discover along the way, like the fact that when you have to compute these weights, that you can actually continue to do it efficiently, even though the weights involve partition functions themselves. And it's even a little more subtle when you have unstable ground states, because then you don't have an expansion to approximate certain partition functions. So you have to use the fact that if you're in an unstable phase, you quickly flip back to the stable one. And if you flip back fast enough, then you can do something very crude to compute what happens in between. But at this point, I think if you can devise a convergent expansion, I would feel quite confident you can also devise an algorithm.
And another stupid question is that, so in statistical mechanics, if you have a convergent expansion, you can compute correlation functions, not only the free energy, but probably computational. People are not interested in correlation function or anything like that.
Well, I think they are also. So here, you're right. Of course, you could use those expansions to compute other quantities as well.
And probably we're more interested in correlation functions than the partition function itself.
Right. So here though, I think the motivation is, it's a little strange to say the motivation for coming up with an algorithm is not to use it, but that kind of is. The motivation is when is computation possible?
Yes.
As opposed to actually carrying it out. Because like I said, these, the polynomials are very high degree, and my guess is that if you tried to use these on a 10 by 10 by 10 torus in 3 dimensions, it would probably never finish running. I mean, practically speaking. But we never computed the degree of the polynomial. I mean, it was that bad.
Yeah. Okay.